Hello everyone, sequence series and proof day number 1 on arithmetic sequence and series as well as geometric sequence and series. To bring a little bit of light onto the subject, arithmetic sequences and series take on a linear pattern or progression, okay, sometimes referred to as an arithmetic progression. And the geometric sequences and series take on an exponential. Okay, exponential or geometric progression. Okay, we're going to refer to these with some of their parts. The linear progression or arithmetic sequence has what's called a common difference. Common difference. Typically referred to as lowercase d, and the geometric has a common ratio, typically referred to as lowercase r. Let's get into some of the details of sequences, and then we'll get into each of these groups. All right, so a little bit about the basics of a sequence as opposed to a series. A sequence is a list of n terms in sequential order. Now, n could be any number, or it could be an infinite set. So n could be infinity, meaning that the set or sequence does not end. So if a sub n is 3n minus 1, then the first term, which is a sub 1, would be 3 times 1 minus 1, which would be 2. The second term, a sub 2, would be 6 minus 1, which would be 5. The third term, a sub 3, would be 9 minus 1, which would be 8. The nth term, if I went out to it, would be exactly what I've got, which is 3n minus 1. Now you'll notice that this looks linear, right, in its progression or in its nature, and it is. This is an arithmetic sequence. You could see that our common difference here is 3 as our function, or it's not a function, as our sequence increases by 3 every single term along the way. Our first term, which is an important term, is a sub 1, which can sometimes be referred to as just a, and that's 2. Okay, so let's look at now the series of the sequence. The series is the sum of the n terms, or in this case, we've determined that this will be the sum of the first 1, 2, 3, 4 terms, right? So if we start here, our iteration starts at 1, and it goes up to this limit of 4. Okay, so this is where we start, n equals 1. This is where we end, n equals 4. So we're going to add up the first 4 numbers. Well, you'll notice that this sequence is identical to the one given above. So we're adding up the terms of this sequence, which would be 2 plus 5 plus 8 plus the next term, which would be 11. That's the first 4 terms. So this is a sub 1, a sub 2, a sub 3, a sub 4, and we're just adding them up. Now, what tells us to add it up is this sigma. Sigma, and that means to sum or to add. So the sum of the first 4 terms would be, looks like 26. Okay, let's look at now sequences and series and their classifications. Okay, so a sequence or series can be classified as either arithmetic, geometric, or neither. An arithmetic sequence, like we said, follows a linear pattern having a common difference d. Geometric having a common ratio r. If a sequence is neither arithmetic nor geometric, then it has an irregular pattern, something that's not linear and not exponential. That would be considered neither. Okay, let's look at a few examples on the next slide. Okay, so let's look at A through D here. Determine whether the sequence is arithmetic, geometric, or neither, and then write its general term, which is just its nth term. Okay, so I see that in the first example, my first term is 2, then 7, then 12, then 17. Clearly, each term is 5 more than the term before it. So my constant difference is 5, or my common difference. This is going to be arithmetic. Now we can write the general term. So the nth term, the way that I like to do this is I like to think of it as a linear function. So I think of it as slope times independent variable plus the y-intercept, or the initial term. Now the initial term isn't the first term, right? A sub 1 equals 2. What would I go back to a sub 0? A sub 0 will be the term that will be used provided that n is starting at 1. Okay, so a sub 0, if I went back 5, would be negative 3. Therefore, now I can write my general term, which would be 5n minus 3. And you could see if I were to plug n equals 1, 2, 3, 4 in there, I would get the correct values that I have in my sequence. Okay, so we said it's arithmetic. It's got a common difference of 5, and it would have this starting point, a sub 0, of negative 3. So here is our general term. And it can be used to construct any term within that sequence. Okay, now one thing that we do need to note is that n is an integer, specifically a positive integer, because we start with n equals 1, right? This set is n equals 1, then 2, then 3, and so on. Okay, so we do need to note that n is a positive integer. Okay, let's look at part B. So it looks to me like this is not linear. It doesn't look to be geometric either, right? I'm not multiplying 1/2 by something to get 2/3. And that same common ratio, it wouldn't apply then to get to 3/4 for the third term. So I'm going to generalize this. I'm going to say this is neither. And I'm going to generalize it. What I do notice is that it looks like I'm adding 1 each time in the numerator. Well, that equates actually just to n. Because if 1/2 is the first term, a sub 1 is 1 over 2, then I could construct a sub n to equal n over n plus 1. Let's see if that works. So this is my second term, so 2 over 2 plus 1, 3 over 3 plus 1, 4 over 4 plus 1, 9 over 9 plus 1. Okay, so I need to know, now, as I noticed this first sequence was infinite, right? So I said n is greater than, or n is in the positive integers, no limit, right? Because the sequence continues forever. Here, this is a finite sequence, so it has a finite number of terms. You can see it ends at 9/10. So how would I determine how many terms there are? Well, it looks like n shows up in the numerator in every term. So this would be the 9th term. Therefore, n is in the positive integers, and n is less than or equal to 9. That's how we would classify that general term. All right, let's look at part C. I'm seeing immediately a common ratio. So if I take any term divided by the term before it, I should get r if that's consistent. So 25 divided by negative 50. Yeah, that would be true. It looks like r is equal to negative 1/2. Okay, so let's construct a sequence here. I'm going to take 100 and multiply it by negative 1/2. Now, I need to make the exponent such that the first term would still be 100. So if the first term, a sub 1, equals 100, then I want negative 1/2 to the 0 power. I want this thing to equal 0. So I'm going to take n minus 1. Okay, so a sub n would equal 100 times negative 1/2 to the n minus 1 power. That's true. It looks like it's an infinite sequence. So when n is in z plus, no limitation on n. Okay, finally, part D. It looks like I've got a common difference increasing by 2 each time, so d would equal 2. My first term, a sub 1, which could be referred to as a, is 1. So I'm going to find the 0th term, kind of that starting point. So that would be, let's go back 2, that would be negative 1. Okay, therefore, I could write the general term, which would be 2n minus 1 when n is in z plus and n is less than or equal to Would that be 99? Okay, outstanding. Ooh, that wouldn't be 99. Hold on, let's rethink that. That's not the 99th term, that's just the number 99. So let's do this. What I'm going to do is find the term number if 99 is the nth term. So I'm going to add 1, which would be 100, and divide by 2. So n would equal 50. So n is less than or equal to 50. There's my general term, and I've got it for all the others above. Well, let's continue with a couple more examples of sigma notation. Okay, example 2, write the following series in sigma notation. Okay, so first of all, I have to determine whether this is geometric or arithmetic or neither. So I'm going to start with I equals 1. That just means my first term will be a sub 1. And I'm going to go up to, let's see here, 1, 2, 3, 4, 5, 6. So 6 terms. It looks to me that the common ratio is -2. So it looks to be geometric. Common ratio is -2, and the first term is -6. So I take my general term, right? So a sub n would equal -6 times -2 to the n minus 1. I just input that in. So I find the sequence general term, and I plug it into the series. And that should output what I want. Let's just check. If I plug in a 1, I get -6 times -2 to the 0. So that's -6. If I plug in a 2, I get -6. Let's see here. Times -2 to the first. So -2 to the first. Okay, -6 times -2 to the second. -6 times -2 to the third, etc. Now, let's see if we get what we're looking for. That would be plus a 12. Yeah, that would be minus a 24. That would be plus a 48, and etc. We're going to get what we want. Therefore, this is the correct setup of sigma notation for that series. Okay, let's look at the second one. It looks like this is actually geometric as well. Looks like r equals -1, and it looks like a sub 1 equals 1. So I could set this up using a series. It looks like it's an infinite series, so I equals 1 up to infinity, okay, of 1 times -1 to the n minus 1th power. Since our first term is 1, we would want n minus 1 as the exponent. And of course, that would output the sum of the values that I see there. Okay, let's see here. Looks arithmetic to me. Arithmetic. Okay, I can see a common difference of 16, increasing by 16. First term is -5. And I would find the 0th term, which would be a -21. And therefore, I could construct the general term. So a sub n would be -5, 16n minus 21. So the series representation of this would be I equals 1 to infinity. The reason for the infinity is because there is no end to this series of 16n minus 21. Okay, let's continue. Here comes the fun part, okay? Now we're going to get into some pure math here. Let's talk arithmetic sequences first. So if I were to write out a sequence just in general terms, I would have a sub 1 plus a sub 1 plus d plus a sub 1 plus 2d, that would be my third term, plus a sub 1 plus 3d, that would be my fourth term. So if I went out to my nth term, I would have a sub 1 plus n minus 1 times d. So I've added the common difference n minus 1 times to get the nth term. Okay, now what we're going to do is write out this is actually the sum of the first. This is the sum from I equals 1 to n of a sub n. That's the sum, okay? Now that is equivalent to the sum of the first n terms, considering that we know it's arithmetic. Okay, so let's write that out right here. That's a sub 1 plus a sub 1 constant difference once plus a sub 1 constant difference twice. I'm going to actually, for space, I'm going to cut out that fourth term, a sub 1 plus n minus 1 times the common difference. Now, a cool proof on how to find the actual sum in general form, they take the second and they flip-flop the order. So they take the nth term, a sub 1 plus n minus 1 common differences, and then a sub 1 plus n minus 2 common differences, right, which would have been the term right before this one. Okay, all the way out to a sub 1. Okay, so what you end up getting, if you add them up, okay, if I added these terms in this orientation, right, and this term here would go with whatever the next term is, what we'll get is we'll get n groups. Okay, so 2, if I added this, I'd get 2 times the sum. If I add these two together, I'm going to get 2a sub 1s plus n minus 1 common differences. Now, if I do that all the way along the way, I will have all the way down to the last one. Okay, and I'd have n of those groupings. So I'd have n of those groupings, 2a sub 1, n minus 1 common differences. And this is how we come up with the general formula. We divide by 2 for finding the sum. Oops, that should be an n minus 1 common differences. This is the sum of the first n terms of an arithmetic series. We can also write this as, and I'll explain in a second, n over 2 a sub 1 plus a sub n. So if I know the first and the last term, and I know how many terms there are, I can use this if I know a sub 1 and a sub n. If I don't know the last term, okay, and I just have enough information otherwise, I can use that formula. Now, where does that come from? Why can I use this red as well? Why are they equivalent? Well, because if I break up these two a sub 1s, and I take one of them, I leave it there, and I add the other one to this, a sub 1 plus n minus 1 times d is actually equal to the nth term. Okay, so it's useful. All right, let's look at example 3. It says a sub 1 equals 5. A sub 15 equals negative 51. Okay, it says find the common difference. Okay, so I'm going to use my formula for the nth term, okay, which is a sub 1 plus n minus 1 common differences. I'm going to find the common difference because I know the nth term. I know the 15th term is negative 51. I know the first term is 5. And I know the number of terms is 15. So 15 minus 1 is 14. So I'm going to subtract 5, which would give me negative 56, and divide by 14. So negative 56 divided by 14 is going to equal d, which will equal negative 4. So d is equal to negative 4. Okay, now I'm going to find the sum of the first 15 terms. The sum of the first 15 terms will follow this formula here. And I'm going to use the second formula, the one in red above, because I know the first term and I know the 15th term. So the sum of the first 15 terms is the number of terms, 15 over 2, times the first plus the last term. Okay, so the sum of the first 15 terms comes out to be 15 halves. And that would be a negative, what would that be, 46. So if I divide by 2, it would be 15 times negative 23, which gives me an answer. The sum of the first 15 terms is negative 345. This is some fun stuff. It's kind of puzzle-like. Let's keep going on example number 4. All right, example 4. And now, guys, for the rest of the lesson, I'm just going to start doing examples, utilizing the formulas that we've developed and just going right through, using some problem-solving skills. Your problem-solving skills might not be as shaped as mine are yet, but the process of practicing, trying, learning things along the way, you'll start to see, kind of where you should be headed. Okay, so example number 4, a sub 1 is -7, a sub 4 is 23. The sum of the first n terms is equal to 689. Find the number of terms n. Okay, so what we want to do is we got to find the common difference first. We're assuming this is arithmetic. Okay, assuming this is arithmetic. So let's find the common difference first. Okay, so the fourth term, 23, should be equal to the first term plus 4 minus 1, or 3 common differences. All right, so if I add the common difference 3 times from the first term, I should get the fourth term. Okay, so I'm going to add, that gives me 30 equals 3d. So my common difference is 10. That's helpful. It doesn't ask for that, but obviously in order to find the sum, I got to know that. So the sum of the first n terms will equal n over 2, 2a sub 1 plus n minus 1 common differences. So I'm going to plug in the values that I know, and the secret here lies in finding n. So that'll mean that 689 equals n over 2, 2 times a1, which is -7, so that'll be -14, plus n minus 1 times d. So since d is 10, I'll distribute. I get 10n minus 10. And now the goal is to solve for n. So I would, if I were you, multiply both sides by 2. That gives me 1378. 1378. And then I distribute and combine like terms. So 10n squared minus 24n. Now the expectation is not that you can factor this. So I would be able to, if I were you, use your calculator, obviously solve where that quadratic equals 0, and then make sense of this situation. Okay, so for example here, I think there's 2 values that come out. One is negative, one's positive. Obviously the number of terms has to be positive, and I believe n comes out to equal 13. So there are 13 terms necessary in order for the sum of those 13 terms to equal 689. Okay, example 5. Clearly here I have a linear relationship between my variable and the constants that are around it. So I'm going to determine then what my first term is and what my common difference would be. So the common difference is pretty easy to locate. That'd be 5. My first term, you just plug in the first value for r on the summation. Plug that in. Looks like a sub 1 equals 1. So I've got my first term, I got my common difference. I can find the sum of the first 28 terms. First 28 terms sum would be 28 over 2. It would be 2 times the first term, so 2 times 1, plus n minus 1, which would be 27, times the common difference, 5. Okay, so, whoops, I should probably write a 5, not d. There we go. So then it's just simplifying from there. So therefore, if I were to simplify that out, I would get, what would that be? 14 times 2 plus whatever 27 times 5 is. I believe I get, oh boy, 27 times 5 is 135 plus 2, 137. And 137 times 14, I believe, comes out to be 1918. All right, there's the sum of the first 28 terms, which is also the sum from r equals 1 to 28 of 5r minus 4. Okay, let's look at some more examples here. Example 6. An arithmetic sequence, or excuse me, series S of n is equal to n times 2n minus 3. What that means, you guys, is that the sum of the first term, which actually is just the first term, would be equal to 1 times 2 times 1 minus 3. So the sum of the first term would be -1. Now the sum of the first 2 terms would be 2 times 2 times 2 minus 3, which would be equal 2. So that's the sum of the first 2 terms. So this is a sequence representation of a series. It's kind of weird. But if you think about this, then S sub 2 is really a sub 1 plus a sub 2. So let's look and find the first 3 terms. We said the sum of the first term which is equal to the first term only, would equal -1. The sum of the first two terms, which would be equal to the first and the second term added together, we know is equal to 2. So if 2 is equal to a sub 1 plus a sub 2, then a sub 2 is equal to 3. So I've now found a sub 1. I've found a sub 2. I can find a sub 3 by finding the common difference. The common difference will always be any term minus the term before it. So in this case, it looks like the common difference is 4. That tells me then that a sub 3 would be a sub 2 plus 4, which will be 7. All right, so in the process, I found part B. The common difference, of course, is 4. Okay, let's keep looking. I think I've got a few more challenging questions here after some geometric work with sequence series. Okay, so geometrically, let's find the sum of the first n terms, which can be written as I equals 1 to n of a sub n. And we're assuming that a sub n is a geometric sequence. So that would be a sub 1 plus a sub 1 times r plus a sub 1 times r squared all the way out to a sub 1 times r to the n minus 1. So this would be the first term, this would be the second term, this would be the third term, and this would be the nth term. Okay, so the proof on how to find the general formula here is kind of unique. It's pretty cool. What we do is we take the sum, which we found here, a sub 1 plus a sub 1 times r plus a sub 1 times r squared all the way out to, and I'm going to write out the n minus 1th term, so a sub 1 times r to the n minus 2 plus then the nth term, which is a sub 1 times r to the n minus 1. Okay, and then in the second portion, we're going to subtract r times s sub n. So that would make the first term a sub 1 times r plus a sub 1 times r squared plus, and then I'm going to continue my series representation out here to a sub 1 times r to the n minus 2, and then plus a sub 1 times r to the n minus 1, and then plus a sub r to the n. Okay, so, and I think I might have said that incorrectly, but if I took each of these terms here, right, so they align, if I were to multiply each of these terms here by r, the nth term would turn into, if I multiplied it by r, I would get this. Okay, if I multiplied this term by r, I would get this. Okay, this term is some term buried in here, the one previous to this one multiplied by r. So it would be a sub 1 times r to the n minus 3. Okay, so clearly if I subtract, please be very careful in recognizing this, this term will disappear, those will disappear, these will disappear, and this will disappear. All right, so what will I have left? Well, s sub n minus r s sub n will then equal whatever is left. Okay, now we need to be careful. This will be a sub 1 minus a sub 1 r to the nth power. So I'm going to factor on both sides. I'm going to factor out an s sub n, which will be s sub n times 1 minus r, and I'm going to factor out an a sub 1, which will leave 1 minus r to the nth power. I divide both sides by 1 over r, which gives me the formula, general formula for finding the sum of the first n terms for a geometric series. Okay, where r is a common difference, or common ratio, excuse me, n is the number of terms, and a sub 1 is the first term. Now, if r is between 1 and -1, that means that the infinite series will converge. If this is not satisfied, then you would not use the formula I'm about to show you. But if r is between -1 and 1, then as the number of terms goes to infinity, this would go to 1. Right? This would go to 0, so this would go to 1. So I get a1 over 1 minus r. This is only applicable, of course, if r is between -1 and 1. Okay, so with that being said, another way that you may see this referred to typically is a over 1 minus r. That's the summation of the infinite number of terms of a convergent geometric series. Now, a series geometrically is convergent if r, like we said, or the absolute value of r is less than 1. These two things are synonymous right here. Okay, the geometric series will be divergent if the absolute value of r is greater than 1, and even to that extent equal to 1. Okay, let's look at a few examples, and then we'll call it good for today. So example 7 says, find the common ratio and the general term. Well, the common ratio is always a to the n plus 1 over a to the n. That just means a term divided by the term before it. So if I took 5 and divided by 5 halves, I would get 2. Would that also be true if I took 10 divided by 5? Yes, that would be true. Therefore, the common ratio is 2, and the general term, I could say for this sequence, would be 5 halves times 2 to the n minus 1th power, considering that n is in z plus, no limitation on it. Okay, on the next one, if I divided any term by the term before it, would that be equal? Yes, it would. This would be equal to r. So r is equal to -1/3, and we can write our general term. Let's do it. So the first term is 9. The common ratio is -1/3 to the n minus 1th power. Which of these two, actually just as a bonus, which of these two series, if I were to write this sequence as a series, which one would converge? The second one would converge because r is between -1 and 1. This one would diverge. We'll talk more about that later. Okay, let's look at a general case, including this variable x. Okay, so any term divided by the term before it should be equivalent if this series or sequence is geometric. And it looks like this comes out to be 2x squared. So r comes out to be 2x squared. So let's write the sequence a sub n. First term is x. Common ratio is 2x squared to the n minus 1. Okay, this could be written in multiple ways. I'm going to leave it like this for now. But what we could do, this is bonus, if we wanted to compress this a little bit more, we could write this as x times 2 to the n minus 1, x to the 2 times n minus 1. And then what I could do is compress the x's. So this would be 2 to the n minus 1 times x to the first times x to the 2n minus 2. And what I can do with the exponents on x would be to add them. So if I took 1 and added it to 2n minus 2, I would get x to the 2n minus 1. Now, this is going further than you necessarily need to unless IB asks you for that form. This would be totally fine right here. No questions asked. All right, let's continue. Okay, so similarly in example 8, as to what we did with the arithmetic sequence to find the nth term, is I'm going to take the nth term, which would be the first term times r to the n minus 1. Okay, so the nth term is 12.15. The first term is 0.15. Our common ratio we just need to find. So we're told, let's assume that this is geometric, but we could confirm it. If this is geometric, these two ratios should be the same. And they do end up being the same. R equals 4, it looks like in this case. Excuse me, 3. Okay, so I plug in a 3 to the n minus 1th power. If I divide both sides by 0.15, I end up getting 81 is equal to 3 to the n minus 1th. Now 81 can be written as 3 to the 4th. Therefore, 4 should equal n minus 1, so the number of terms should be 5. This is our 5th term. Okay, let's look at a very similar example in the next one. our first term. So let's take the nth term, 4.296875. No calculator on this. Ha, funny. 440. It looks like our common ratio is 1/4 to the n minus 1th power. Okay, so what I got to do here is kind of interesting. What I'm going to do is divide both sides by 440. And if I do that, I'm not going to write down the number, but I get an ugly number here. It's like 9.76 to the 10 to the negative 4th power, okay? And over here I get 1/4 and to the n minus 1. All right, so I'm going to take the natural log of both sides. I'm going to take the natural log of the ugly. And I'm going to take the natural log of 1/4 to the n minus 1. That allows me to bring n minus 1 down, okay, using the power rule of exponents in the natural log. Okay, now I'm going to divide. So I'm going to take natural log of ugly divided by the natural log of 0.25. That's going to equal n minus 1, so then I'm just going to add 1 to this value over here. That should give me n. Of course, I'm using a calculator here. That was really funny. And if I do that, it looks like I get 6. So you're telling me that this filthy pile, natural log of ugly over natural log of 0.25 is equal to 5? Yep. All right, so it takes, looks like this would be the 6th term. Okay. Let's look at example 9. This looks like a fun one. First term is 4. Common ratio, -2. Find n if the nth term is -2048. That was a fun game back in the day. Was it called 20? Yeah, it was called 2048. All right, so -2048 is equal to 4 times -2 to the n minus 1th power. All right, so I'm going to divide by 4. That gives me -512 is equal to -2 to the n minus 1th. Okay, so -512 is actually equivalent to -2 to the 9th. If -2 to the 9th is equal to -2 to the n minus 1th, then 9 is equal to n minus 1. Therefore, n should equal 10. Okay, if you needed a calculator or some help here to go from -512 to -2/9, you should start playing more 2048 or, yeah, I don't know. Okay, let's continue. Example 10, a sub 4 is 54, a sub 6 is 486. Find the common ratio R. Okay, so R is equal to a sub 5 over a sub 4, right? And R is also equal to a sub 6 over a sub 5, excuse me. So R squared is equal to a sub 5 over a sub 4 times a sub 6 over a sub 5. So the a sub 5's reduce, giving me that R squared is equal to a sub 6 over a sub 4. Well, I have both a sub 6 and a sub 4. A sub 6 is 486. A sub 4 is 54. That ratio comes out to be 9. Therefore, R is equal to plus or minus 3. There you have it. All right, let's continue on with a couple of more examples. Okay, example 11. Find the sum from 1 to 5, the first 5 terms of that series. So the first thing I need to know is I need to know the first term. First term will be 3 if I plug in a 1. I need to know the common ratio. Common ratio is 2. And the number of terms, which is 5. So the sum of the first 5 terms will be the first term times 1 minus R to the nth power all over 1 minus R. Okay, so the sum of the first 5 terms, if I just use some algebra, will be 3. This will be a -31 over a -1. It looks like that sum, given above, will end up being -93. Okay, let's look at example number, positive 93. Whoa, watch out now. Example number 12, find the sum, the infinite sum Now, the infinite sum only exists if r is between -1 and 1, which it is. So I got to find the first term. My first term, if I plug this in, will be 2 times 1/2 to the first power, which is 1. My common ratio is 1/2. So the infinite sum of this series does exist because r is between -1 and 1. It'll be a over 1 minus r. So the sum given above will be 1 over 1/2, which is 2. Okay, let's look at 13. I think we got 13, 14, 15, and we're done. All right, problem number 13. This is a doozy. It's kind of fun. But you know what? Struggle through it. Maybe try this on the side and see what happens. So S sub 2. S sub 2 is a sub 1 plus a sub 2 in any series, right? The first term plus the second term. So a1 plus a2 is equal to 20. Okay, then the sum of the first 4 terms, S sub 4, is a1 plus a2 plus a3 plus a4. So the sum of those first 4 terms is 1640. Okay, so if a1 plus a2 is 20, then a3 plus a4 will equal 1620. Okay, so why is that helpful? Because a3 is equal to a1 times the common ratio twice, and a4 is equal to a2 times the common ratio twice. Okay, so why is that helpful? Well, because now I know that 1620 is equal to a1 times the common ratio twice, plus a2 times the common ratio twice. So I can factor out the common ratio, which gives me r squared times a1 plus a2. All right, so let's do a little work here. If a1 plus a2 is 20, then r squared is equal to 81, which means that r is equal to plus or minus 9. Pretty outstanding there. It does say find, though, the 2 possible geometric sequences. So let's look at if r is 9. All right, so I know the first 2 terms added together, that sum is 20. So the first term I don't know, and I don't know what it is, but I do know that 1 minus r to the second over 1 minus r should give me the formula for the sum of the first 2 terms. Okay, so as I simplify this, I'm going to multiply both sides by -8. That gives me -160 is equal to a1 times -80, right? Because 1 minus 9 squared is -80. So a1 is equal to 2. Therefore, one of the sequences, a sub n, would be the first term 2 times 9 to the n minus 1th power. Okay, so there's one of my possible geometric sequences. The other one, I would take 20 is equal to a1, 1 minus -9 to the second, right? R is now -9 over 1 minus a -9. So that would give me 200 if I multiply both sides by 20. a1, 1 minus 81 again, which would be -80. Okay, so a1 comes out to be -2.5. All right, which leads me to my general sequence being -2.5, -9 to the n minus 1th power. There are 2 possible geometric sequences for example number 13. Okay, let's look at number 14. Number 14, it says a geometric series is given by the following. S sub n equals 7 to the nth minus 1. It says find the first term. Well, the first term will be equal to the sum of the first term itself. So that would be 7 to the 1 minus 1. So the first term is equal to 6. It also says find the common ratio. Well, we know the common ratio is the second term over the first term. So if I can find the sum of the first 2 terms, which is a1 plus a2, the sum of the first 2 terms would be 7 to the second minus 1. And I know a1 is 6, so I can find the second term here. So that would be 48. That's the sum of the first 2 terms is equal to 6 plus a2. So a2 must equal 42, So R will equal A2 over A1. So it looks like our common ratio is 7. All right, one more example here, and that'll be it for today's lesson. Okay, example 15. For what values of x will the series converge? Okay, so anytime you're asked if a series is convergent, it is going to be an infinite series. So you can see I've got an infinite series here from term 1 up to no limit. So if that's true, the common ratio has to be between 1 and -1. And in this case, the common ratio is equal to 1 plus x over 2. Right? That's being iterated exponentially. Therefore, it's the common ratio. So we want 1 plus x over 2 to be between 1 and -1. First thing I would do is subtract 1 from both sides of the compound inequality, which would give me the following. X over 2 has to be between -2 and 0, not inclusive of those endpoints. Right? Now I'm going to multiply both sides of the inequality by 2. That gives me that fact that x must be between -4 and 0 in order for the series to converge. Any value between there works. That's it for today, guys. We'll see you in day number 2.